This video is for Physics of the Universe, Unit 1.1, Understanding and Describing Motion. Today's essential question is, how can physics use Newton's laws of motion and universal gravitation to predict objects' motion? Hello, baby birds! Today, we're going to connect a hands-on, real-world event, the annual Pumpkin Trebuchet launch, to some of the most profound ideas in science. Now, picture this. A 250-kilogram counterweight drops rapidly, swinging a long arm that hurls a 5-kilogram pumpkin through the crisp autumn air. The path it travels, how high it goes, how far it flies, none of that is random. Every part of that motion is governed by Newton's 3 laws and his universal law of gravitation. These principles don't just apply to pumpkins, they explain how satellites orbit, why apples fall, and even how we get to other planets. So let's decode the invisible rules that shape everything in motion. To understand the rules of motion, we need to meet the man who first described them, Sir Isaac Newton. Born the same year that Galileo died, Newton revolutionized science in the 1600s by showing that the same set of laws could explain both earthly and celestial motion. His book laid the foundation for classical mechanics, the very mechanics that guide every part of our Pumpkin Trebuchet's launch. Without Newton, we wouldn't have the math or physics to calculate the pumpkin's range, its peak height, or its impact speed. His work unified falling apples and orbiting moons under a single framework, the laws of motion and gravity. Newton's law of universal gravitation tells us that all objects with mass attract each other with a force. That includes Earth and our airborne pumpkin. The pumpkin's flight may look like a simple arc, but it's actually a battle between inertia and gravity. Gravity constantly pulls the pumpkin toward the center of the Earth, curving its path downward into a classic parabolic trajectory. The formula, which you see represented on your screen here, F sub g is equal to big G multiplied by m1 multiplied by m2 divided by r squared, gives us the force of attraction. The more massive the objects, the greater the pull. The farther apart they are, the weaker the pull, by the square of the distance. Our 5-kilogram pumpkin is tiny compared to Earth's 5.98 times 10 to the 24th power kilograms, but the effect of gravity is significant. This force not only determines how long the pumpkin stays in the air, but also where it lands. It's essential to understand that mass and weight are not the same here. Mass is how much matter an object has. It stays the same whether you're on Earth, the moon, or in space. Weight, on the other hand, is the force of gravity acting on that mass. Our pumpkin has a mass of 5 kilograms. On Earth, its weight is calculated by multiplying its mass by Earth's gravitational acceleration. So weight is going to be equal to m times g here, which is 5 kilograms multiplied by 9.81 meters per second squared, which comes out to be about 49 newtons. But if we were on the moon, where the acceleration due to gravity is about 1.6 meters per second squared, its weight drops to only 8 newtons. That's why astronauts and pumpkins feel so much lighter on the moon. However, the trebuchet would still need to overcome the same inertia in order to accelerate the pumpkin at the start, because inertia depends on mass, not weight. So let's scale up from our pumpkin to celestial bodies and see how Newton's gravity law works for the Earth and the moon. How can we use Newton's law of universal gravitation to calculate the gravitational force between Earth and the moon? If we plug in the values, right, that we know here And note, if you're going to do a calculation like this on a test, you will be given these values, or you can write them in your notes to be sure. The mass of the Earth is 5.98 times 10 to the 24th kilograms. The mass of the Moon is 7.35 times 10 to the 22nd kilograms. The distance between them would be 3.84 times 10 to the 8th meters. And then big G is always 6.67 times 10 to the 11th Newton meter squared over kilogram squared. Then we compute. Let's start by just looking at the two masses. Let's multiply them. 5.98 times 10 to the 24th multiplied by 7.35 times 10 to the 22nd ends up being 4.39 times 10 to the 47th power kilograms squared. Then we'll multiply what we just calculated by big G. So 6.67 times 10 to the 11th power multiplied by the 4.39 times 10 to the 47th power comes out to be 2.93 times 10 to the 37th Newton meters squared. Then we'll bring in the r squared. So 3.84 times 10 to the 8th power meters squared comes out to be 1.47 times 10 to the 17th meters squared. And then we'll take that value and divide. So once we divide our numerator by our denominator, we have solved for newtons. In this case, 2.0 times 10 to the 20th power newtons. This gravitational force keeps the moon in orbit, just like gravity pulls our pumpkin downward throughout its flight. The same rule applies, just on a much smaller scale for our pumpkin contest. Newton's laws are remarkably accurate, but not perfect. They begin to break down at very extremely small scales, like atoms and electrons, where very high speeds, which approximate the speed of light, get pretty close, or in accelerating frames of reference. For our trebuchet, we're working in the range of everyday masses, sizes, and speeds, so Newton's laws are great. But what if we analyze the pumpkin's motion from the frame of the rotating arm, meaning the rotating arm of the trebuchet? That, if you remember, is a non-inertial frame. So to apply Newton's second law there, we'd have to introduce a fictitious force, sometimes called an inertia force or centrifugal force, in order to account for the apparent outward push that we feel. While our pumpkin doesn't go relativistic, understanding these limitations reminds us that Newton's laws are powerful but not absolute. Newton's principles aren't just for textbooks. They guide the real world. Engineers use Newton's second law, which is F is equal to ma, in order to design everything from skyscrapers to roller coasters. Space agencies use gravitational slingshot maneuvers, which is based on Newton's gravity law, in order to steer spacecraft with minimal fuel. Athletes use instinctive understanding of parabolic arcs every time they throw a football or shoot a basketball. And yes, a pumpkin chucker uses the projectile motion equation in order to calculate range. Do you want the pumpkin to fly further? Then increase the arm length. Adjust the launch angle closer to 45 degrees, or reduce air drag. All strategies are grounded in Newtonian physics. So let's summarize everything we've learned so far in this video. First, gravity depends on mass and distance. The more massive the object, and the closer it is, the greater the gravitational pull. Second, mass and weight are not the same. Mass is constant, but weight changes based on gravity. Third, Newton's laws, especially F is equal to ma, let us predict motion in all sorts of contexts. While they break down at quantum and relativistic extremes, they're incredibly effective in everyday scenarios like our pumpkin launch. Finally, the most powerful takeaway is this: the same laws that govern a pumpkin flying across a field also govern the moon's orbit and the motion of galaxies. The rules of physics are universal, and understanding them gives you the power to predict the future, one parabolic arc at a time. At this point, you should be able to generate a full and appropriate response to today's essential question. How can physicists use Newton's laws of motion and universal gravitation to predict objects' motion?